So first of all, welcome everyone for this one more session of Laser Talks webinar series. This is a very small initiative by Laser Science where we are trying to bring a lot of experts, and this is a knowledge sharing basis where we all try to exchange our knowledge here and try to gain some knowledge and experience from the experts. So so first of all, today's topic is dealing with femtosecond lasers. We know femtosecond lasers has been quite active in the R&D and scientific research, like spectroscopy and other things. But equally, nowadays, femtosecond lasers are making quite a big impact on the commercial and the industrial applications. This is because it's a unique pulse duration, high energy, and high repetition rate, which is making the heat affected zone in the interaction of the materials very less. And also, this is also making the process of precision in various materials. So I also want to give a very brief outline about Workshop of Photonics, where our speaker is coming from today. This is a company who's actually having an expertise in making femtosecond micromachining systems for various applications. They are very specialized on the glass processing. And the topic today by Dr. Antanas Urbas is also going to touch upon one of these applications to give this highlight about the specific application. Now, I want to give a very brief outline about our speaker, Dr. Antanas Urbas. He did his PhD in 1978 on natural sciences, which comes under physical chemistry, with a wide, vast experience and technical expertise having. And he joined Workshop in 2015. He's one of the most senior member who's trying to give strategic developments on different applications. And he also plays a very key role in partnerships and collaborations with different companies and different entities. He has been, apart from the current position, he has been a chairman of the Lithuanian Space Association. He was also the sales director of Baltics on the 3D Center, and he was also the country manager of Alcatel. So it's a very unique opportunity because Dr. Urbas also has a dual degree. He has a physics master's in physics and also chemistry. I think this is one of the reasons why he can make unique applications work by his strategic thinking and expertise. So we are all eager to listen to Dr. Urbas. And just one note to the audience is that if there are any queries, please put it in the chat box. The speaker will try to address all these queries at the end. And also, if possible, please input your email as well. So in case we are missing out some clarifications, we can send those clarifications in detail to your email. Once again, welcome you all, and thank you very much for your participation and registration here. I welcome Dr. Urbas on all our behalf. Over to you, Dr. Urbas. We are eager to listen to your talk.
Thank you for your welcome. And I'm really happy to see this many interested in what we have to say. So just not taking very much time, I jump to my presentation. So I hope you can see it.
Yes, Dr. Urbas, please go ahead.
Okay. So today I would like to present you our understanding and our achievements in glass processing by ultra-short laser pulses in the field of dicing and TGV, most related to the glass. And we will talk about why it is glass and why it is interesting. So very briefly, what I would like to talk about. Short introduction, who we are, laser dicing, how it is done, tricks, how to make dicing as perfect as you can, and WOP examples of dicing, TGV, why the market is keen to introduce through glass vias, and why it is important. Just briefly to present how these are made by selective laser etching, because it is most popular way of doing it these days. What parameters are important for process optimization, and again WOP examples of TGV in various glasses. So briefly, who we are. As it was already presented, we are working more than 20 years in the field of femtosecond laser micromachining, developing processes and machines which are implementing these processes. And why femtosecond? It is very simple answer. No material can withstand femtosecond laser pulse. So we have several patent families. Actually, we are roughly 50 professionals, some PhDs, most are Master or Bachelor of Science. And we not only make machines, but also we continuously work on the research and development together with scientific institutions we are in close contact with. What laser applications can we consider? So we are very strong in laser micro drilling, which can be applied to transparent media like glass, sapphire, silicon in this transparency window, ceramics, optical fibers, metal, plastics, whatever. Laser micro cutting, surface structuring, laser welding, laser micromarking, multiphoton polymerization, waveguide writing in 3D shape, and fiber black grating writing. As it was mentioned, we have quite big expertise in glass fabrication. So our most recent focus is through glass vias on wafer and panel size. Very popular and demanded thing is optical fiber arrays for positioning fibers in the mixed electro-optical devices. We also provide glass guide plates for probe cards, microfluidic chips, packaging glass products, glass paces, carrier wafers, glass ceramics and whatever cutting, and microwell plates. So it's plenty of applications, we have to say. Then let's go to our topic. I'll start from dicing. What glass dicing laser means? That first of all, if we have mechanical dicing by means of diamond blade or diamond wire, it makes quite wide curve, which means material loss and quite high value of chipping on the edges of the curve. Meanwhile, laser dicing, I have to mention that both these photographs are made with the same magnification. So you can see that it is much more precise and clean. So as it is non-contact process, there's no contamination with debris. It's clean and flexible manufacturing. As you can see, it is very, very little curve. So meaning you almost lose no material. But of course, if you deal with glass, you have to be careful taking into account glass material features. How it usually happens? So going from right side to the left side. So it can be glass can be separated by ablation from the top side or from the back side. Each of these methods have their advantages and disadvantages, but the main thing in this ablation approach is that you have removed material, and which means that there's plenty of particles flying around and settling on the surfaces, and you have to clean it afterwards. If you make this scribing or dicing, whatever you call it, so you make modification in the glass material, and then adding mechanical force, would it be bending on the sharp edge or stretch tape, you simply mechanically separate your material along these dicing lines. So again, here you can see main stages of laser dicing. So one thing is to place it very precisely in the according to the drawing you have. You make internal laser modification and then separate it mechanically. What are most popular and most efficient methods to induce modifications for dicing? Quite old method is stealth dicing. How they call it is Hamamatsu, which is used by Disco company. So you introduce damages inside of glass. If it is thick workpiece, you place multiple scans, and then you simply break along this this line. You can do it on one go in quite big thickness. So if you use the effect which is called filamentation, it is patented by Rofin Sinar. What is filamentation? It is combination of plasma defocusing of the beam, which is focused inside, and Kerr effect focusing it again. So you have, like here, you should have many passes to get several damage lines. In filament, it is made automatically. So it is focused, defocused, focused again, defocused again, focused again, and you have a filament, a chain of modifications along the focus line. So it is quite precise, and again you can break after one single scan. And we love it most, and I think most patents are related to this very right side process, is using non-diffracting beams. For instance, it can be a Bessel beam, where you have elongated focus through the entire thickness of your workpiece, and you make modification through all thickness, and you simply move your workpiece relatively to this beam position, and you break it again. And we have patent on it. Corning has plenty patents of its Trumpf, whoever. many companies were working on it, and I think it started in 2000 when it became very popular approach, and now Corning alone has roughly 120 something patents related to Bessel beam application in glass. So just to tell to those who don't know, and to remind who knows it, how the Bessel beam is arranged. In contrary to Gaussian beam, where the parallel beam, collimated beam is focused into one single spot, which is very well known, described having relay length of the waist and minimal radius of the focus. So if you place, instead of spherical lens, if you place conical lens, which is popularly called hexagon, it forms a needle, quite long needle, which can be millimeters, centimeters long, and you just have to adjust its dimensions to your workpiece to get a modification along this line. So what is important that this minimum dimension of Bessel beam is 3-4 times less than you can achieve with the same optics in Gaussian beam. So meaning that it is no big deal to get 1 micron thick needle to modify the glass. So meaning that you are much more precise than you would be while having a Gaussian beam focus. So, what is important when you put this laser beam into the glass with the purpose of achieve cutting line, meaning to perform dicing. So, laser parameters are very important, but what we should start from, sorry, I put it a little bit below, but the main thing which you have to take into account is which glass it is it coated, uncoated, if it is on tape, what is the tape, and you have to take it into account to select pulse duration, energy, repetition rate, overlap, so which has impact on the cracking and joining the modifications, and of course beam delivery control is also very important, meaning polarization, beam shape, focus depth, and so on, and so on, and so on, and so on. So it is very multi-parametric task to be solved. Sorry. Oops. Okay, so as I mentioned, very important thing is beam shape, which is related to the stress which is induced in the glass volume. So if we see that when we place Bessel beam pulse focus as Bessel beam on glass, in the top we can see very nice, very round spot, which looks very smooth. But if we go a little bit deeper, in this case it's 200 micron under the top surface, you can see that it is quite irregular. And often it has quite unpredictable form. And if your beam is shaped poorly, you can see how it looks inside of the glass. This video shows you modifications and cracks every 50 microns going down to the top surface. You can see that there are sometimes very well-defined directions of the cracks, but these are not the same on different depths. And what happens if you try to make dicing with such badly shaped beam? Surprise, surprise, cut line cannot be formed because these cracks inside of the volume are in very different directions on each spot, and they simply cannot join. And this a line of separate modifications, but no single cutting line. So what we can do to make cut line efficient and nice? Again, there are several patents which make this possible and good. All of them make this modification elongated desired direction. So it can be done by means of cylindric optics. It can be done by means of phase elements, like in Corning patent, and we use variable space variant retarders to shape the beam to achieve this elongated form in the damaged area. So, and if you can see that if you like it was in the previous direction, deviating from your desired cutting line, they are not joined. When you direct them in the same direction, you have a cutting line. And this should be quite precise joining, because this deviation is roughly 10 degrees, and you can see that the cracks do not join. And in this Corning picture, you can see that if these modifications are directed in proper way, you can find the distance between modifications when the cracks are joined very well, and you can build separation line. So it means that knowing how you produce stress in the glass volume, you can control the process of preparing cutting line, and afterwards your mechanical effort will make quite clean and nice cut. So now a little bit pricing ourselves. What WP can do and can provide you if you need it in dicing. So as I mentioned, we have quite good experience in dicing of transparent materials like glass and sapphire. It is this example presents D236T glass, which is quite popular glass for semicon applications. And you can see that the cut surface is quite clean. Fused silica, again, very nice. Sapphire it is not so nice with a little bit bigger chipping because of being crystalline material, and this crystallic planes pull a little bit your cuts into the material. So that's why it is not so clean like glass, but still quite good. And again, our patents are related to temperate, non-temperate glass, sapphire, so whatever you want. And we extended this experience to other materials. The main thing is that material must be transparent to laser light. If you remember this forming of the Bessel beam, there are beamlets coming from the cone from Hexagon. They have to penetrate into material to build this needle. So meaning that material must be transparent. So if we work in transparency window for silicon carbide, or coated glass, we can achieve chipping better than 10 micron. Normally it is a couple of microns. We can do it in all shapes. And of course, we can tune dicing process for different thicknesses. Today, we safely work with scribing speed up to 300 millimeters per second. And single pass can be as deep as 2 millimeters. So, I already saw several questions about dicing, and some answers will come a little bit later. But now, let's go to the second part of our meeting. It is about TGV. TGV stands for through glass vias. Why it is interesting and where it is expected to be used. So here you can see ideal view which is created by APEX. It is European initiative for creating next generation packaging of 3D electronics. So you can see a lot of layers which should be interconnected in the big structures and in the single chip, which is 3D layered chip, processing unit, memory, and all this connecting to the power and to further elements. And the best interconnect is made through glass, just now. So again, what is TG through glass via? So it is opening in the glass, which is filled with conductor. In most cases, it is copper, and it interconnects elements on one side to other side in the best possible way. So what it is in terms of production? So we take glass, we make laser modification, then we go to wet etching. This is most popular way of creating TGVs in the market today. Then we check with automated optical inspection and give it to metallization, where seed layer is set on the surface and inside of via, and copper is put into the via. Afterwards, of course, should be removed from surfaces. So we in WOP, we stop at this stage. We have some kind of optical inspection, which is not really automated. So that's why if we need big structures, we ask our partners doing it. But where are we strong, and what I will be telling you about, it is up to the stage, meaning making modification in glass and etch it through. Just a small talk about why TGV, why glass. You can see what Intel says about it, that organic substrate is not very flat and not very smooth surface. And it is not very stable in dimensions, because plastic is plastic, you see. And the electric performance is not so good, quite high dielectric losses because of dielectric constants, and it is very well seen at high frequencies, especially talking of 5G and 6G. The loss in the plastic is quite big. If we use glass instead of, so what we have, it is very good flatness of the substrate. It is 100 angstrom, 10 angstrom, whatever you want. It is just depending on your polishing quality. The electric loss is much lower than in plastic. And you can select glasses which match very well with silicon, meaning that if you place your silicon chip on this glass core substrate, thermal expansion is the same. You don't lose the contact. You don't have bigger losses, electrical losses in this package. And of course, one very important thing is that the glass allows much higher density because of being able to provide a couple of micron wide interconnects between layers. So if we go to TGV, what is important if you want to go to the market saying, hey, I can make TGV, what they will ask you? As I mentioned, we have to take into account that it will work in gigahertz range. So meaning that the form should be as smooth as possible, meaning that it should be straight, minimal ratio of face to top and bottom. Top and bottom should be the same. And roundness should be, if perfect is good, but it should be better than 90%. And the roughness of inner wall should be 150 nanometers or better. So, selective laser etching, as I mentioned, is now the main stream for making TGVs. And this two-step process, first creating 3D structures inside transparent materials by means of femtosecond laser, and then modified material is selectively removed by chemical etching. It is a multi-parameter process, and which starts from dependency of material properties, meaning if you have borosilicate glass or alumina silicate glass, alkali, non-alkali glass, and it defines these parameters very much. So these are all dependent on in which material and what you have to achieve. Again, this is a two-step fabrication process. And what I have to mention that it is selectivity of etching, meaning that etching speed for laser modified material and non-modified material should be as high as possible. It I have many slides presented, I guess, last year about it, but believe me that it is a very, very complicated process, and if you have to select the best optimal windlass and this particular shape you want to you have to achieve. So just to showing you what is important. So if you put too little energy, it might be you don't achieve modification big enough to be etched selectively. Moderate, so you can make these modifications that can be efficiently and smoothly etched. If it is a little bit too high, then you can build nanogratings or cracks, which help you in etching, but it makes your shape irregular and very often unpredictable shape. So again, compared to what we saw in the bad shaping of the beam, here you can see what we can make with quite proper and very specific shaping of the beam in polarization profile and energy distribution along the beam. You can see that this crack structure inside of the volume is not very regular, but also it can be considered as being almost the same size along all the path. So and this gives us quite good result. So what is important to say that as I mentioned, the people from semicon and especially from electronics, they ask for very smooth surface. But selective laser etching cannot make the surface in very, 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 very smooth, meaning RA 100 nanometers or something like that. So you can see that with no regard, is it acid etched or alkali etched via, the surface has a kind of a bubble structure. Several microns on the surface, and let's see what it is in the depth. So if we look at side wall, you can see that top peak to valley is approximately the same. Would it be KOH or HF etching? It is roughly 800 nanometers. Not perfect, but quite good for the purposes the industry asks from us. Now, how WOP makes it. So what we are specific and what we are known about, that we make space variant retarders that help us in shaping beam, especially non-diffracting beams, in the form we want to use for our purposes. So this is a diagram of retardance and fast axis measurement in the element. So you can see these are two sets of rings which are shifted to one to another. It results in non-diffracting beam having elongated shape, which is very important, as I showed, if you want to get clean line in dicing. If you want to have it even more elongated, you may make the element this kind, and you will have, like we call it, optical knife. It's quite wide in the wide direction and very narrow in X direction structure. You can make very good cuts, and you can imagine that the cracks will propagate in this direction very well. So this is our pattern. Now, about TGVs, which we make by means of our very special optics. So you can see this is a photograph of the cuts of the TGVs. These are quite regular, quite uniform, meaning that the waste ratio to top to bottom is 95% or so. And it is over 330 micrometers, which is again quite popular size of the substrates. So how we achieve it? So as I mentioned, it should be optimized in energy, shape, duration, and then what optimization means. So if we take difference just in duration, these photographs show difference in duration. It is one length, it's double and triple duration of the pulse. You can see that longer duration at the same energy, meaning that peak fluence was least here, 3 times lesser than here. So you can see that the diameter of via is very well dependent on the duration or peak fluence. Now we can change polarization patterns due to our special elements, and these are results as the same laser pulse parameters and etching conditions constant. So you can see that different polarization patterns give you very different results in the shape and size of the via. And again, a little bit of self-pricing. So we got, I think it was in the show in Taiwan, people said that our vias are the best quality. They say, we believe. So you can see quite big variety of glasses we work with, and all of them are considered as very good candidates for glass core in semiconductor industry. These vias were etched in alkali etchants, in acid etchants, and what is important, we can ensure that no bad vias appear across all the working area. You can see the parameters what we can provide. And here are some examples of how these vias can look like. BF33 Borofloat is, I think, the best glass for making vias. You can see very regular shape, very uniform along the depth. EXG alumosilicate non-alkali glass is not so nice. If you see the cross section of the via, it is a little bit elliptical, more sensitive, but it is very hard to get roundness 98%. Here is, let's say, it is 100%. But it is so hard glass, but we can handle it as well. So D263T, so you can see also here automated optical inspection photographs. You can see quite straight vias where the waste ratio to the top or bottom is more than 80%. And here is an example that we can make areas of vias 5 microns and a little bit less. So, and now we are already preparing, we have an in-house machine which can handle, oh, sorry, it is 510 millimeters, not 5 meters, which can handle glass panels. And we are probably early autumn, we will be ready to supply first machines to the customers. So, okay, I left some time for questions, luckily. So just small conclusions that laser fabrication, as you see, brings and presents precision and quality to glass dicing and TGV formation. And combined with wet etching, laser fabrication enables to make whatever you want and whatever an industry needs. It is worth mentioning that beam shaping in space and time helps a lot, but it adds a lot of degrees of freedom. So you have to plan very carefully what you want to achieve, and you have to know very well what is changed if you change this and that in parameters. So that's why process optimization for multi-parameter process is a quite long deal. And you not always know whether you reach the absolute or local maximum of quality. So that's why my cordial suggestion is to take licensed technologies if you don't have time and personnel which can do it for your own. So questions, as we agreed, I will see and I'll try to answer as many as I can from the chat. The rest will be sent to you by mail where the mail is provided. And then, thank you for your attention. And now I go to the chat, if you allow me.
So, are you able to see that from the chat, Dr. Urbas, or should I read it for you?
I can try. You know, I'm not very familiar. I'm not very familiar with this Google.
Okay, so the chat.
Okay,
okay.
I see the chat. Okay. The question from Sudhir, it was first one. So glass processing by femtosecond laser, it is not automatically clean. So it depends on how your beam is shaped, related to your next question. So if you if you join the cracks you create with your Bessel or modified Bessel beam properly, you can have very, very, very smooth surfaces, as you can we're seeing in the photographs. So Bessel beam helps in this process that you have to place only one shot per full depth of the of the your workpiece. And Hexagon Apex, I will share these slides with you so you can see what it is. What is the maximum thickness of glass? Again, it depends. It depends. It depends how many drills per second you want to make. So 10 micron holes we made in, I think it was half a centimeter thick, something like that. But it takes very long. It is not made by single shots with Bessel beam. It is just pulling your damage along the your etching line. So it depends. So thickness is related to other requirements. So speed and precision. Wall roughness, I showed it for selective laser etching, and for dicing, again, it depends on the what requirements were. So meaning curvature and the speed which you need to achieve. So it is 1 micron and less. Precautions to be taken in semiconductor processing for clean cut. That is usual precautions. It is clean room. It is good removal of all the materials which can pop up from your workpiece, and it is in the best case it is in inert atmosphere. Special optical elements for diffracting beams for our patent or whatever else patent. Yes, you can purchase it separately. You just have to know what this element should make. And if you don't know the design, we most likely we will provide you with the design. And later, when we agree the design you can test if it works as expected. This is not very much related to today's talk. 2.5 millimeters on stainless steel. Is it diameter or it is thickness? Both is possible, but it is not with the equipment, with the optics I was talking about today. 500 micron hole with 2.5 millimeter deep. So including in this case 500 micron hole, it is multi-shot case, so it will be, I think, laser process will take will be something like 20 holes per second, but much longer process is etching it. For 2.5 millimeter is quite long. If you want to have straight walls, it takes again which material. For fused silica, it will take several hours. For borosilicate glass, it takes roughly 1 day etching. I mean, for these aluminum silicate glasses, it may take a couple of days. Gaussian pulse, this is not question, this is statement. Yes, we know that these stresses are remaining, and our customer has pointed at it, but we had the measures, and the residual stress is reduced to minimal. Yes, as I mentioned, this rotational orientation, not the hexagon lens, but our specific elements which produce modified Bessel beam with elongated shape or many beamlets in one line. It is very important. Again, we come to 10 microns in 1.5 millimeters. Yes, and again, it depends on glass. I need to know the material. Then I can tell you a little bit more precisely. So, but for any, yes, we can. Taper angle for 10 micron, it might be up to 5 degrees. Yes, all the refractive index effects affect the process, as I already mentioned. So it can even go to filamentation and other unwanted or wanted effects. So how to decide the direction? Usually we rotate the element which creates this dedicated direction. Time.
That's a question, continuity of the 10 micron over 1.5 millimeter. He says it's for a borosilicate glass, and he's asking what is the time.
So everything is connection.
Connection is going off. Okay. So, so I think Antanas is uh, looks like he's disconnected. Okay. So then I'll wind up this meeting. Is that okay? Or yeah. Okay.
He was trying to join.
Okay.
Maybe Jagdish, if you have his number, you can text because he would like to complete, I think.
Okay. So meanwhile, I think I've seen a lot of queries coming from Sunil and a lot of other people's. Dr. Dixit, of course, he wrote a lot of queries as well. So,
Yes.
and I request everybody to please give your emails. Our team wants to also circulate certificates for this participation. So please give your email IDs so that we can also give you a participation certificate in this regard. And if there are any more queries, you can also please send it by email and we will try to get these answers. It will also be useful for us to send you some slides so that we can be in touch. So I'll wait for a couple of minutes for Dr. Urbas to join. In case no, then looks like I will end this call then. And thank you very much. So it was a very nice talk. Actually, it spoke about an optical knife with a chemical etching process. So again, as I was saying, the expertise was from physics and chemistry background. So you use the laser knife and the chemical etching to get, and this talk was really enlightening. I hope the same for everybody also. And we sincerely thank everybody for joining this. We do also request you to join in a lot of webinars and so that we are just sharing knowledges between us and somewhere we can create a spark of our own. Thank you very much and have a nice day. So with this, we wind up this webinar session. Thank you very much.
Thank you.
Okay, thank you.